So greetings from Nebraska. I will talk about spin-orbit torque in metallic bilayers and trilayers with first principles calculations used as a tool. So here's a brief outline. I'll say a couple of words about the mechanisms of spin-orbit torque, then on to the methodology and the results for bilayers and then trilayers. So this is a typical device structure for a spin-orbit torque bilayer. We have a layer of heavy metal that has strong spin-orbit coupling and a ferromagnet, and thanks to charge-to-spin conversion, the current that flows in the plane gives rise to a torque acting on the magnetization, which can be used to switch the magnetization or drive high-frequency precession or move skyrmions or other spin textures and do lots of interesting things with magnetic dynamics. There are a couple of simple mechanisms that are well known for the spin-orbit torque. So one is the Spinhole current, which is generated from the heavy metal and gets absorbed by the ferromagnet, which leads to this kind of angular dependence. This is called a dampinglike torque, and its angular dependence looks like this. Another effect is the inverse spin galvanic effect, also called the Edelstein effect, which appears due to the development of a non-equilibrium spin accumulation in the surface bands, which can exert torque on the adjacent magnetization through an exchange field. And this leads to an angular dependence that is called the field-like torque, which acts just like an external magnetic field. But there are other mechanisms that can contribute to the spin torques, which have come to prominence recently. So interfaces can themselves generate spin currents due to the interaction of the electronic spins with the K-dependent effective magnetic fields at the interface. Ferromagnets themselves can generate spin currents of various kinds. There are intrinsic and extrinsic mechanisms that may need to be taken into account. And there may be symmetries beyond damping-like and field-like torque. And we'll see one of them in the following in this talk. In addition, spin torque structures typically are strongly disordered, so there is no clear separation of length scales. The thickness of the layers, the mean free paths, and the spin diffusion lengths can all be of the same order of magnitude. So this makes it more difficult to apply phenomenological models. And on top of this, in trilayers, as we'll see in the following, there can be crosstalk between different layers due to mean free path effects that can lead to additional types of spin-orbit torques. All such mechanisms can be captured by material-specific ab initio simulations in realistic disordered systems, and such calculations can be used as sort of a computational experiment with results suggesting new mechanisms, and they can be compared to simpler models to understand which processes are the most important in a particular system. So a couple of words about the methodology. We use the non-equilibrium Green's function formalism. There is an active region where scattering happens, and this region is attached to the leads that can have different electrochemical potentials. One can calculate the lesser Green's function, which can be used to evaluate the expectation values of observables, such as the torque, which is described by this operator in DFT. And a disorder can be introduced explicitly in the system by taking a sufficiently large supercell for the active region, introducing disorder in the form of either Anderson random potential or substitutional alloying, or whatever you want to include, and then averaging the results over the configurations of that disorder. So here's a benchmark for this calculation. The Spinhole conductivity in platinum. So we will take a non-magnetic system, just a film of platinum. And from this spin continuity equation, one can recover the spin current flowing between any two layers in the film by evaluating the expectation values of the spin orbital torque and summing them up from the vacuum to the given layer. So if one does that calculation for a 100 monolayer platinum film, these are the results that we get. So this is the spin current as a function of the position inside the film for different amplitudes of Anderson disorder. And then the value of the spin current in the middle of the film usually is simply equal to the Spinhole conductivity. If backflow is important from the inhomogeneous profile of the spin accumulation, it can be subtracted, but there is no need to do this in most cases in a film this thick. So this is the result for the resulting spin current flowing in the middle of the film. As we see, there is this characteristic shape with a peak at the Fermi level and the negative conductivity in the regions below the Fermi level. There is very little dependence on disorder. There's a little peak here, but this is actually due to backflow. And we can compare this with the calculation of the intrinsic spin-hole conductivity from the Kubo formula. This is pretty much just the integral of the Berry phase over the integrated part of the filled part of the electronic bands. And we see that the shape is very similar. The amplitude, the magnitude is actually also quite similar. So what this tells us is that the spin transport in platinum is consistent with the intrinsic mechanism. So essentially no disorder dependence, and agrees with the Berry phase calculation. But note that this is a very different kind of calculation. There is no linear response calculation here. It's just a disordered platinum film, and we explicitly calculate the spin current and average it over the disorder configurations. So it's quite reassuring that it reproduces the known result in platinum, where the spin-hole effect is believed to be due to the intrinsic mechanism. So one more tool that we need to analyze the spin-orbit torque is how to represent its angular dependence. So it can be quite complicated in general. It can go beyond the damping-like and feel-like terms. So we use the orthonormal basis of real vector spherical harmonics to represent this dependence. This is a set of functions that is known from electrodynamics. Each of these harmonics, those are vector functions. Each of them has a definite parity on the time reversal, either even or odd. And there are two types of these functions. Type 1 is purely damping-like, and it can contribute to magnetization damping and affect the width of the FMR resonance. Type 2 is purely feel-like, which means they are derivable from an energy functional. And notice that the feature of being damping-like and feel-like does not come along with parity on the time reversal. So the leading damping-like term is even in magnetization, for example, but as you go to higher values of L, the parity will alternate. So these are the first few harmonics. The 1 minus 1 type 1 is the damping-like, and the color here shows the contribution to damping. So it's proportional to my for the damping-like, this lower harmonic. The feel-like torque is the lowest order allowed harmonic type 2. And then we'll also meet with the planar-Hall-like harmonic, which is shown here. It's type 2-1. Type 1 indices 2-1. So it's actually odd in M. but it's damping, and it contributes to damping as this MXMZ product. So in practice, we calculate spin-orbit torque on multiple points on the sphere for multiple orientations of M, and then the data can be projected onto the set of these harmonics because they're orthonormal. That unambiguously determines each term individually. So now switching to the results for the bilayers. This is a typical setup. So this is a cobalt platinum bilayer. There is vacuum separating this part of the system from its periodic images. And then Anderson disorder is introduced here to tune the resistivity of the system to where it is experimentally. One can also use substitutional disorder, which we used for a different work, which I'm not going to talk about here. This is just for an illustration of the band structure of the system. As you can see, very complicated. So one needs to use first principles calculations to get an accurate result. So this is the result for the angular dependence of spin-orbit torque in this cobalt platinum bilayer. Each arrow here shows a calculated point. And here the even and odd parts are separated. We can see that the even part looks essentially like the conventional damping-like torque. All the arrows point to towards the y-axis. The odd term is more complicated, and this is the dependence on the disorder strength. Less disorder on the left, more disorder on the right. So the even part looks pretty much the same. The odd part does change a lot. And the reason is that the odd part contains both the field-like torque and the C21 harmonic, which is the one I showed on the previous slide. That's the planar-Hall-like harmonic. So here are the results of the projection for different disorder strengths, so more disorder to the right. First, we see that the damping-like component is essentially independent of disorder, which is consistent with the expectation based on the intrinsic mechanism. The field-like torque, which is this line here, it's appreciable at weaker disorder, but gets strongly suppressed as disorder is increased, which is also expected from the Edelstein effect. And finally, we have this planar-Hall-like harmonic, which is also appreciable. It's considerably smaller than the leading damping-like term, but it is appreciable, and it also, like the damping-like component, essentially independent on disorder. So we'll talk about it a bit later. Let's first look at the thickness dependence of the damping-like torque. So spin diffusion model gives this sort of thickness dependence for the damping-like torque generated by the Spinhole effect. So it starts from 0 in the limit of 0 thickness of the normal metal layer, and then it saturates at the length of the order of the spin diffusion length. And this is the result of the calculation for two systems and two different disorder strengths. So what we see here is that this damping-like torque does not go to 0 as the thickness of platinum is sent to 0. So there appears to be a finite intercept, and we have to interpret this here as an interfacial contribution, as opposed to the bulk contribution that looks like this. So we have to add a constant here to the fit, and this represents this interfacial contribution. And the results of the fit show that the interfacial and the bulk terms are comparable, and in fact, the interface term can even be larger. So this means that there are mechanisms that are not reduced to the bulk Spinhole effect that can generate damping-like spin-orbit torque in a bilayer. The results for the Spinhole angle and the spin diffusion length are generally in the range seen in an experiment. So let's look at the planar-Hall-like torque then, which is the non-trivial angular dependence that I mentioned before. So again, as I already explained, both the leading order dampinglike and this planar-Hall-like torque are essentially independent of disorder. The thickness dependence of the planar-Hall-like torque is similar to the dampinglike torque. At least we see that it increases with thickness. There is some noise here because it's small. Notice it's scaled up by a factor of 10, but it generally correlates with the leading dampinglike torque. And we can also probe the origin of this term by turning off spin-orbit coupling in different parts of the system. And it turns out that if we turn off spin-orbit coupling in cobalt, then essentially nothing happens to these two terms. But if we turn it off in platinum, then both of these terms are strongly suppressed and essentially become zero. So this tells us that the source of both of these is in platinum. We know this for the dampinglike torque, but for the planar-Hall-like torque, it tells us that this effect in our calculations actually doesn't come from the planar Hall effect in cobalt, which requires spin-orbit coupling in cobalt. There were measurements of this planar Hall-like torque using ST spin torque FMR by Safransky and co-workers in this paper. So they measured the line width, current-induced line width change in two planes. The XY plane here is sensitive to the dampinglike torque, and the XZ plane is sensitive to the planar-Hall-like torque. So the ratio of the two, if we calculate that from our results, it is in fact quite similar to the results for the platinum ferromagnet system that they used, but they also see this effect of a similar magnitude with gold and palladium. In our calculations, the effect in those systems is much smaller. So this suggests the mechanism could be different. And the two possible mechanisms that have been proposed is the planar Hall effect in ferromagnet that somehow generates spin torque through the longitudinal spin accumulation. It's not quite clear how that happens, but it seems generally consistent with the experimental results. The other possibility is the Spinhole effect in combination with anisotropic interfacial spin relaxation can also lead to this effect, as was shown in this paper, and our results appear to be consistent with this mechanism. So there's only a small amount of data available experimentally and theoretically as well, so more work is needed to understand the mechanisms of this effect. So now I'll turn to trilayers. So trilayers can add more complicated symmetries, which is essentially the interest in studying them. For things like field-free switching, it's important to break certain symmetries. So let's consider what kind of torques we can expect in a system where we have two ferromagnets and perhaps the source is in one part of the system that can generate spin currents and whatnot, and then there's a detector that will respond to that. So generically, if we look at the torque on layer 2, we can imagine or expect that it's a combination of a damping-like and field-like torque, but the orientations of the polarizations for those terms can depend on the magnetization of the other layer. So one can write an expansion like that. So for example, S here is the Z cross E, which is the Y direction with the standard choice of axes where the current flows in the X direction. So the terms proportional to S will just give the conventional torques that exist and the only ones allowed in a system where there is no other ferromagnet. But there are additional terms here, and many of them have a known interpretation coming from various effects, coming from the generation of the spin current by the ferromagnet or its interface with the normal middle. But there are also two terms here that are non-conventional. Those are non-local M1 dependent field-like torques acting on M2, so they contribute to this F2 here. And these torques are essentially absent in spin diffusion models, or at least they're expected to be very small. Now, as we'll see, these torques are actually possible and can be sizable, and they can result from interlayer crosstalk or mean free path effects. So essentially, electrons sampling both magnetic layers before getting scattered. So this is a similar mechanism that is instrumental in the current in plane GMR, which is the effect that sort of started the spintronics field. So first, let's look at the torques acting on each layer for parallel and anti-parallel orientations of the magnetizations. So similar to the case of CIP GMR, where the conductance depends on the relative orientation, we see here that the torque acting on each layer depends on the relative orientation of the two layers. So this is not expected in the spin diffusion model, but the effect is very large, especially when disorder is weaker. And the giant magneto-torquance ratio can reach a few 100%. So this is sort of reminiscent of the CIP GMR, and it declines with the thickness of copper. So with this in mind, I want to focus on the torques and the angular dependence of the torques while keeping the two magnetizations orthogonal. So I minimize the input from the CIP GMR into the results. So in this way, all the angular dependence will come from different ways the spin-orbit coupling gets itself into the business, rather than through the dependence of the relaxation times on the relative orientation of the magnetization. So if we pick a certain direction of M1 and we turn off spin-orbit coupling in the second layer, we can calculate the torques acting on M2, and we'll know the source of that torque is somewhere in M1. This helps understand the mechanisms a little better, and one can always add the two kinds of torques coming from spin-orbit coupling in different parts of the system. So we consider the cobalt system here. We did this for permalloy as well with similar results for this torque, but I'll focus on this one. And we can calculate the two components of the torque acting on M2 as a function of the angle that M2 makes in the XY plane. And this is what we get here. There are two components. The component proportional to the cross product of the two magnetizations is conventional. One can show that it comes from the Spinhole effect generated either by the interface or by M1 itself. So I'm not going to focus on that because it's conventional, but the other one is unconventional. This is the blue line here. It's a component of the torque that is parallel to M1. And this component is not predicted by the spin diffusion model. At the very least, it's expected to be small because it requires both a precession of the spins at the interface here and an imaginary part of the spin mixing conductance here. So neither of that is expected to be large, but this term is actually very competitive with the leading Spinhole-like torque. So one can do this for different orientations of M1, and overall one can fit this torque to this form. And this form is equivalent to this contribution to the effective field induced by the current in magnetization M2, which is odd in M1 and goes as cross product M1 cross Y. So to understand this, we have done semi-classical simulations using the Boltzmann equation. So this is a collaboration with Vivek Amin, who did these simulations. So in this calculation, all the layers are, for simplicity, assumed to have the same spherical Fermi surface. So the magnetism comes through spin-dependent and spin flip impurity scattering. So the linearized Boltzmann equation looks like this. So it has the electric field part and the spin precession around the exchange field, which controls the absorption of the spin current flowing into the ferromagnets. So this is the impurity part. And then one adds the bonds, which account for all sorts of permutations of the spin current that can happen at the interface. And that is an essential piece of the puzzle. So those come through the boundary conditions. And those are obtained from the simple model for the interfacial potential. So then all of this is solved numerically. And indeed, we can get a angular dependence of the torque that is similar to what we found in first principles calculations. Now, the magnitudes and phases do depend on various parameters, but one can find reasonable parameters where this angular dependence is reproduced. And importantly, the amplitude of this term that is proportional to M1 declines exponentially as the thickness of the normal layer gets larger compared to the mean free path in the normal metal layer. So it comes from crosstalk of the two layers on the scale of the mean free path. How does that happen? So here is the mechanism that we propose to explain this. So here we recall that because there is a spin polarized current flowing in layer 2, and the normal metal layer is not large compared to the mean free path, this current leaks out into the normal metal, and it can reach the interface with the other ferromagnet, and that interface has spin-orbit coupling, and it can transmute spin current into different components. So this current parallel to M2 can get converted through those interfacial processes into the out-of-plane spin current, which is polarized parallel to M1. Then get that current, reaches the interface with M2, and gets absorbed to the spin transfer mechanism. But because it depends on M2 to begin with, there's an extra dependence that turns it into a field-like torque. So this is essentially the mechanism. So to summarize, ab initio calculations present a realistic spin-orbit torque analysis tool, and I showed you some results for both bilayers and trilayers. We can look at these papers for more details, and these are my collaborators and acknowledgements. So thank you for your attention. I'm happy to answer any questions.
Great, thank you very much, Kirill, for a beautiful talk. Do we have any questions for Kirill? Yes, yeah.
Hi, Kirill, this is Can Avcı. Thanks for this nice talk. I have a question. So when you explained, I think it was in slide 17, that in the diffusion model, you don't expect, no, maybe earlier. Yeah, here. So the torque tau 2, which is basically parallel with M1, right? Then you said that this is the unexpected torque that you try to explain. But I mean, if you do like a current, CPP GMR experiment, then you would expect this torque to occur, right? I mean, if you inject a current along the z-axis. and why not?
Yeah, but this is not CPP. This is CIP. The current
Yes.
flows parallel to the interfaces.
But again, I mean,
yeah, so
in that case, you would, I mean, the current that goes through the copper arriving at the cobalt, then I would expect it to be polarized along the M1 such that it can be scattered at M2 to give rise to the GMR. So I don't know if I'm missing something important, that why we do not expect a spin current with the component parallel to M1?
Well, this component is possible, but you can just write the spin diffusion equations with proper boundary conditions, and you can see what kind of components are expected. So the dominant component that we always expect, that is polarized as in the Spinhole effect. So this will be the spin current flowing perpendicular to the interfaces with the spin polarization along Y. Okay, so if it just gets absorbed, it would give you torque in the Y direction. Or if there is an imaginary part of the spin mixing conductance, it will give you a component rotated about M2. Now, one can also get a rotated component that is a cross product of Y and M1. And that can generate this, torque in the direction of M1, but it's supposed to be small because there are two small parameters. Now, there is no current polarized along M1 in the absence of M2. It's just forbidden. If you remove M2, there is no spin current flowing in the Z direction with the polarization of M1. So it can only appear through the interaction of M2 and M1. It's just the way the CIP current geometry works. So this is the reason.
Okay, maybe a follow-up question then. Well, I mean, yeah, I could not follow 100% your, the last couple of slides, but you basically explained that the leakage current basically that goes out of M2 reaches the interface with M1 and then comes back to apply torque. So that's what you are suggesting. Okay.
Yes.
And what about this spin current leakage? So if that happens at M2, it could also happen at M1 with the polarization parallel to M1.
Well, this current flows in the plane. So this arrow, the bigger arrow shows the direction of the current, and the smaller arrow is the spin polarization. Okay. So it's not that this current flows in the direction perpendicular to the layers. It's just that because of the finite mean free path, this boundary becomes kind of fuzzy, right? So this current leaks out in the sense that the boundary is smeared out. So this is still a little bit F2. Okay. So this tail then gets converted at this interface, and this requires spin-orbit coupling here. Remember, we turned off spin-orbit coupling everywhere here. So if there was spin-orbit coupling here, then everything could be converted on either interface, right? But here, spin-orbit coupling is only allowed here. Okay, so here, this current here gets converted into the current that flows out of the plane. There's nothing like that here. So this interface cannot convert an in-plane current into an out-of-plane current. Okay? Now, there is a torque acting on M1 as well. I just didn't talk about it, but the same processes would lead to unconventional torques acting on M1. So if spin orbit is allowed everywhere, there will be both kinds of torques, right? But if we turn off spin orbit coupling here, then leaking of the current from M1 does not get transformed into anything else. It would just be an in-plane current with the spin polarization, and that's it. So if you turn off spin orbit coupling, there is nothing, right? This requires spin orbit coupling.
Okay, thank you.
Any other question? Kirill, I have one quick follow-up question. How does the model depend on the interface details when you have in realistic experimental systems defects and so on?
So in this model here, the boundary conditions come from this model potential. So this is a delta function, and as a function of z, and there's an exchange in spin orbit coupling. So if you tune these parameters, those boundary conditions will change. So this is going to be material specific parameters. But we did calculations in first principles for different systems, and the effect is generically strong. So permalloy, copper, permalloy, cobalt, copper, cobalt. We also tried cobalt, platinum. Cobalt, the effect is much smaller just because of the spin relaxation in platinum. But the things that are going to change are the relative amplitudes and the phases of these curves. So the fact that here it looks like more like a sine is material specific. So the phase can change. But the fact that you will get a torque that is collinear with M1 acting on M2, this is generic. Okay, and this is beyond expectations from the spin diffusion model.
Okay, thank you. If there, you have more. Okay, if there are no more questions, let's thank Kirill again.
Thank you very much.